In today's experiment, the RS circuit, you are going to be studying the following inductor that is going to be connected in series with a 10 ohm resistor and the output source of the science workshop. But moreover, we are going to study two different configurations. In the first configuration, the central core of that inductor is going to be free space, while in the second part of the experiment, the central core is going to be an iron core, and we are going to study the differences between these two setups, between the setup where you have free space as a central core and whenever you have iron core as a central core. Starting with the first configuration. So in the first part, what you are going to do is you are going to be connecting the inductor and the 10 ohm resistor in series with that output. So one connection that goes from the terminal across the inductor and the other connection that goes across the 10 ohm resistor. But then again, you want to measure the voltage responses across each of the inductor and the resistor, meaning that you want to study the exponential increase and decrease of the voltage across the inductor and across the resistor. For that matter, you are going to bring a voltage sensor and you are going to connect it across the connections of that inductor. So one connection that goes on that border and the other connection that goes at the other periphery of that inductor. Then you bring another voltage sensor and you are going to connect it now across the terminals of the 10 ohm resistor in order to measure the voltage response or the voltage variation across that resistor. Now over here you are going to be opening the RS software and then you are going to click on start. So as we can see over here we have three different exponential plots for each of the inductor, the resistor and the output source. So over here we have the following plot which is for channel B. Channel B is basically connected across the inductor. So over here we are actually witnessing the exponential increase and decrease or the charging and discharging cycles across the inductor. So as we can see for the inductor, we are starting at a maximum value which is expected. So we are starting at a maximum value and then that inductor is undergoing an exponential decrease until it reaches 0. Then over here all over again, it's going to undergo an exponential increase. So if we look over here at the bottom, it is undergoing another exponential increase until it reaches its maximum, then followed by another exponential decrease, so on and so forth. Now for the second plot, which is for the voltage sensor that is connected across channel A, meaning connected across the resistor, as we can see over here, we also have an exponential increase, like we have different cycles for the exponential increase and decrease across the resistor. So whenever the inductor is starting at the maximum value, at the maximum voltage, the corresponding resistor over here or the corresponding voltage across the resistor is going to be starting at the 0 value for the voltage. So if we look over here, we are starting from that value of the voltage and then it is undergoing an exponential increase until it reaches its maximum value. So over here when it reaches the maximum value, therefore the corresponding voltage across the inductor, as we can see, is actually minimal. It's actually 0. So once it reaches its maximum value, it's going now to undergo a decay, an exponential decay. So from that point onward, as we can see over here, we have an exponential decay across the resistor, which is going to be countered by another exponential increase over here across the inductor, so on and so forth. So as we can see, the inductor and the resistor, they actually function in an opposite manner to each other. Whenever the inductor is undergoing an exponential decay, the resistor would be undergoing an exponential increase, and whenever the inductor is undergoing an exponential increment, therefore the voltage across the resistor would be undergoing an exponential decay. And finally over here we have the voltage of the battery, the voltage across the battery. Now in that part, what you are going to do is basically you are going to be highlighting an entire cycle, an entire decaying cycle for the voltage across the inductor. And for that cycle you want to determine the time constant. So let's say we are going to be highlighting the following decaying cycle, which starts over here from that point. First off, let's try to enlarge that figure in order to view it better. So as we can see over here, we have the following exponential decaying cycle that we want to highlight. So you click on that point and you highlight that entire cycle. Then over here you are going to click on fit and you are going to choose the inverse exponent. Now that inverse exponent, you are going to be recording the value for the C exponent, which is 1930. So C exponent in that case, it represents what? It represents 1 over tau. So that constant over here, that value of C, it represents 1 over tau. So in order to get tau in that case, the time constant, you are going to be taking the inverse of that C exponent in order to determine tau. Then you have to repeat the same thing all over again now for the second discharging cycle. So we are going to move over here to that second decaying cycle, and also you are going to highlight it. All over again, you click on fit, you have to choose the inverse exponent, and now we have another value for C exponent. As we can see, it is actually compatible with the first one, which is logical and expected, which is 1930. So in order to find tau, the time constant of that decaying cycle, you have to take the inverse of that C exponent. And the same thing for the third discharging cycle and the fourth one. So for each discharging cycle, you are going to highlight it. Then you are going to choose fit inverse exponent in order to find that C exponent, which corresponds to 1 over tau. And then in that case, you take the inverse of that C exponent and you would find the time constant. So on that lab report over here, in that first box, or in that first table, you are going to be recording the values for C. The fit constant is none other but the C exponent. So over here you have 4 values for the C exponent, for which you are going to determine the corresponding values for the tau constant, and like I said, tau would be 1 over the fit constant. Then after finding the 4 values for tau, now they ask you to determine the average value along with its error. So you have to apply the standard deviation and the standard error in order to find the average and later on find the error on the average. But first off, they ask you to find T theoretical. So later on you want to compare your average value of T experimental to the value of T theoretical. So we know that T theoretical for an RL circuit is actually equal to L over R. However, what is R in that case? R is not going to be only the resistance of that resistor, but R is also going to take into account the resistance across the inductor. So the inductor, it has its own internal resistance that you want to determine. So you are going to bring that multimeter and you are going to connect that multimeter across the inductor in order to get the value for the resistance across the inductor, the internal resistance. And then over here you are going to be switching the scale to ohm. So as we can see, we are reading a certain value of around 8 ohm for the resistance across the inductor. So the inductor, it has a certain internal resistance of 8 ohm. Therefore, the total resistance across that circuit is going to be the resistance across the resistor plus the internal resistance across that inductor. Now in the second part, we are going to move on to insert an iron core in the middle of that inductor. So we are going to bring the following iron core and we are going to place it in the middle, and then we are going to be connecting the circuit in the same way it was initially connected. So what would be the difference in the case? So as we have seen before, the inductance, which is the tendency of an inductor to resist or to oppose the change in the electrical current, the inductance, it depends on the magnetic flux. So in that case, since the inductance and the magnetic flux, they are directly proportional to each other, therefore when you place an iron core, which is a ferromagnetic material, an iron core is actually going to minimize any loss of magnetic flux to free space. Therefore, the magnetic flux generated by that inductor is going to increase, and as a result, this is going to lead to an increase in the value of the inductance of that inductor. Therefore, we are going to expect for the time constant in that case to undergo an increase whenever you place an iron core in the middle. So over here, you are going to click on experiment and delete all data runs. All over again, you are going to click on start, and as we can see, we have different cycles, different exponential cycles, whether for the decaying or for the increment across each of the inductor, the resistor, and the output of the power source. So if we have a look at the voltage response across the inductor, we can see it is starting from a maximum value and then undergoing an exponential decay, while the corresponding voltage across the resistor is actually undergoing an exponential increase, which is logical. So these two electrical elements, they behave in an opposite manner. One has an exponential decay, while the other one would be having an exponential increase. Then over here, the exponential increment across the inductor is going to be followed by an exponential decay across the resistor, so on and so forth. In a similar manner to what we have done before, in that case, you are going to be determining the time constant of a completely discharging cycle for the inductor. So what we are going to do is we are going to be highlighting that entire discharging cycle, and then you are going to be recording over here the value for the C exponent. So as we can see now, the value for the C exponent, it has changed. It became 469. Therefore, tau, which is 1 over C exponent, is going to be bigger than the previous tau, which we have determined in the case where we didn't have an iron core placed in the middle. Then in a similar manner over here, you are going to be highlighting the second discharging cycle across the inductor, and then you are going to be determining the corresponding C exponent. However, over here, as we can see, the value is not correct, meaning that your highlight for the complete discharging cycle is not correct, so you have to repeat it. Okay, so now we have gotten a more logical value. So now we have 466 for the C exponent. In order to find tau, you take the inverse, then the same thing across the third and the fourth discharging cycle across the inductor. So after finding all of these values, we are going to move to the second part. You are going to fill that table with the values for the fit constant. Then you are going to find the corresponding values of t. Then over here you find the average along with the associated error, which is going to be the standard deviation and the standard error. And then you are going to be deducing over here the new value for the inductance. So after inserting the iron core, now we have a new value, a different value for the inductance of that inductor, which you have to determine it. However, you have to determine it along with its corresponding error, which is going to be none other but the propagation of error. And that would be it for our experiment of today.